Okay, today we're going to talk about, so from today onwards, all the while we did only univariate, like one outcome only, one predictor, right? Or just compare two variables. Today we're going to go into a multivariate from here onwards. Your PhD or master's, only the multivariate counts. What I did earlier, just to understand the basic concepts. Right, let's revise shortly what he did on simple linear regression previous week. So there are two variables. Is it bivariate?
Yes.
Why call it bivariate?
Two.
There are two variables. Bivariate is X and Y. Example we did was BMI versus SBP. So what are the steps we did? We did scatter plot. What's the purpose of scatter plot? What's the purpose of scatter plot? How do you written here, right?
To see if the data is associated.
To see the pattern of association. Is it increasing? Is it decreasing? Or is it random? Next, these are plots we see. Number one, how do you describe number one? How do you describe number one? Come on, response fast, we're still behind time. Yeah.
Positively associated.
When X increases, Y increases equally.
That's all. Right? Number two.
Yes. When X increases, Y decreases.
Number three.
It's random.
There's no association.
No association. Yeah.
Positive association, negative association, there's no negative. No association. Right, correlation. We discussed correlation. Ranges from -1 to +1. This is just wrong. So it should be this way. These are extreme cases. We don't see extreme cases in our studies. Right. This -1, there's a max minimum. +1, there's a max. So what do you see here? As X increase 1 unit, this decrease 1 unit. Same thing. So we're not interested in the extremes. We're only interested in the middle. Now, if the dots are like this, then we can visualize they belong to the center here. Now, what do you say? There's no association. If there's a pattern, it'll move this way. The further it moves, we say very positive. Go this way, very negative. If patterns like this, then we say no association, correlation, right? So any values within -0.3 and 0.3, we assume they are very close to 0. This by Cohen's criteria, it's called effect size. Right, according to him, correlation must be at least 0.3 and above. Right, of course, you don't expect 1. Or can be -0.3 and below. So we are looking for the green areas. If it falls in the yellow area, that means there's no association. So green area, how far away from 0? Here say weak. Here say moderate. Here say strong. Right? Same way to opposite side. Next, we went to regression. In regression, we wanted to fit a line. The line that best represents the dots. So what's the method called? What's the method called?
Regression.
The regression, what's the method called? O?
Linear
OLS.
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 Ordinary least square.
Ordinary least square.
Square what? Square of
Square of residue.
what is residual? What?
The observed minus the predicted.
Distance between observed and the value on the line. Right? There's a method called that. Basically, you want to know the line y equals to b0 plus b1 x. Right? So these two are the b0 is where it cuts the y-axis. b1 is a slope, and x increased by 1 unit, how much the y changes. So we call it slope. So we are actually interested in the slope. This b0, just for making prediction, once you put the x in the b1 plus the b0 to get the y, right? We don't explain the b0, we explain the b1. So what's basically testing? Is the slope 0 or not 0? That's all. Is the slope 0 and not 0? Now, if the lines comes this way, slope 0 or not 0? Slope, is it 0 or non-zero? You understand
Zero.
slope, right?
Zero.
You understand what is slope, right? Class,
Yeah, gradient.
gradient. Is there a slope?
Yes.
Is there a slope? We put a ladder against a wall. Does it look like this? Ladder against a wall. Does it look like this?
Yes.
Does it look like this? Put a ladder against a wall. Can it look like this?
Nope.
What happened? What happened to the ladder?
Fall. Drop.
It will fall. There must be a base. The base is constant. And the slope. Compare slope 1, slope 2. Compare slope 1 and slope 2. Answer 1 and 2. Differentiate. Compare slope 1, slope 2.
Slope 2 is steeper than slope 1.
Slope 2 is steeper. So what does it mean? Slope 2 steeper than slope 1 means what? B value will be higher here compared to here, right? That's a slope, isn't it?
Yes.
Basically, it tests whether the slope is 0 or non-zero. Now, how do you explain the slope 2 compared to slope 1? Okay, slope 2 compared to slope 1. How do you compare this? How do you compare slope, red slope compared to blue slope? How do you interpret the blue slope? Gradient is 0 or non-zero?
Non-zero. Non-zero.
Non-zero means what?
Red is 0.
I increase, right? Blue means as X increase, Y increases, right?
Yes.
Red means what?
0.
As X increase, does Y increase?
No.
Now, what about this? What about this slope?
A negative value.
Negative means what? Explain sentence.
When X increases, Y decreases.
When X increases 1 unit, Y decreases by how many units?
100.
Right. So this or this, are they 0 or non-zero? These two, blue and red, are they 0 or non-zero?
Non-zero.
Non-zero.
Both are non-zero. Now, what about this red? 0 or non-zero?
0.
0 means we say Y does not depend on X. The blue line means the slope is not 0. In this case, it's more than 0. Then it says Y depends on X. If the slope goes this way, is the slope 0 or non-zero?
Non-zero.
0 is less than 0. Now what do you say? Does Y depend on X?
Yes.
Yes. Y depends on X, but negatively.
Negative.
Just now, positively. And the middle will be, I draw one more, the middle will be 0. So that's why evaluating. The slope is a blue, is a red, or in the middle here. When this one comes in, we'll say Y does not depend on X. When you get this, Y depend on X. As X increases, Y increases by 7 units. This one also say your Y depends on X. As X increases by 1 unit, Y decreases by 7 units, right? So that's what we did in simple linear regression. Right, look at this now. So this is a positive slope. This one 0. Compare number 1 and number 3. This be stronger, this weaker, right? Isn't it?
Yes.
Yes.
So what's the residual? Which one will have a bigger residual? 1 or 3? Which one will have a bigger residual?
3.
3 bigger residual, the 1 very small residuals. So this r square will be high. This r square will be low. What's r square? What's r square?
Correlation coefficient, is it?
No. R square. Let's see what's r square. Okay, that's a residual.
Prof, can I answer?
Yeah.
R squared is the sum of the residuals squared.
No. Okay, let's see now. This is a residual. Right? These are residuals. Can be positive, can be negative. So this is a method used OLS. So all the residuals minimize is the best line. Let's go to I go to the table. Partition the variation into regression, residual. The total is partitioned in these two. The total variation, all the residuals squared and added. If I know this, and I know this, how much must be regression? How much?
90.
90.
90.
Right? This we know from the graph, all the deviations. So the total minus the residuals, that's what you get there. It's not somebody said r square is the sum of the residuals. No, it's not sum of the residuals. Let's go to what's r square.
Is it
That's
regression over residual times 100%?
Regression over
Regression over residual times 100%.
the mistake in the notes. That's a mistake in the previous notes. It's not explained over unexplained. Can you correct it? Huh? It is explained over the total. Right?
Okay.
Yes, Prof.
Are you okay?
Yes,
Yeah,
Prof.
Prof. Yes, Prof.
Is explained over the total, right? If regression, if this is 100, this is 10, then what's the r square? What's r square?
90%.
90%. This must be 90, right? So 90 over 100. So this 90 and this 100. So what's r square? What's r square?
90%.
90%. Ranges from 0 to 100. 90%, is it good? 90%,
Yes.
is it good?
Yes.
Almost 100%, right?
Yeah.
Yes.
That will be like graph number 1. The residuals are very small. Supposing, on the other hand, this is 80. What must this be?
20.
20. That's what's r square?
20%.
20%. Is it low?
Yes.
And then your graph will be something like the third one here. Right? The r square tells you how strong your model is. What's r square? Percentage explain variation. Why I call explain? Why I call explain?
Because it's explain variation.
It does explain, there must be unexplained, right? It does explain, there must be unexplained, right?
Yes.
And are you teaching English? And
Yes, sir.
what's the opposite I explained?
Unexplained.
Unexplained. So this is explained regression. And this must be
Unexplained.
unexplained. The unexplained actually is what? Residual, right?
Yes.
Unexplained is actually residual. So what it means is, I don't know why the dots are away. I can't explain this. The model does not explain why the dots are not sitting on the line. So that's a percentage unexplained variation. So that's the R square. And the assumption we have in simple linear regression is that the collection of the residuals must be independent and normally distributed, right? What do you mean by independent? The graph must be like number one. Number one. Yes, number two, number three, number four are violations. Violations of randomization. Random. The graph comes like this. You can say, yes, they are. The residuals are independent. If your graph comes like 2, 3, or 4, there's a violation of the assumption. That means your model is not valid. That means this model is not valid because why? This is violated. The second one, normal. We test whether normally distributed. We've gone through what's normal. We check the normality test, whether p-value more than 0.05, then it's the assumption met. Right. So we did an example comparing BMI and SBP. So we did scatter plot to see visually. So what do you see here? Elena, what do you see here? Explain. Elena?
Yeah, it's random.
Huh?
I can see, yeah, like when the BMI increase and the SPB increase as well.
Say again. What is this axis? What is this?
Sorry, I'm working. Yeah, I can see when the BMI increase and the SPP increase as well.
Right, this BMI. The higher the BMI, the higher SBP. Is there a pattern? Is there a positive pattern?
Yeah, I can see the line.
Next question is it strong or weak? We do correlation. In the correlation analysis, the correlation value between BMI and systolic BP is 0.669. 669. Adib ko? Not there.
If made, yeah.
Is it Adib ko? Adib ko is not around. Michelle?
Yes, Prof.
Explain this, interpret this. This is a correlation value, right?
Yes.
Between body mass index and systolic
And SBP.
SBP. Is it small or is it big?
It's big.
Small is considered small. Say I put here.
Yes.
Is it more than 0.3?
Yes.
Yes. And is it significant? What's the p-value? Is it significant?
No. Yes.
It's less than 0.001, right?
Yes.
So we state the correlation value are 0.0669 and the p-value is less than 0.05. There is a positive association between the two. The higher the BMI, higher the SBP. And see this one more than 0.3. That's why I said the range for correlation Right, that's the range for correlation. 669, does it fall somewhere here?
Yeah.
Right. We say the strong positive association. So first, we visualize. Okay, first step, we visualize. Second step, we correlate the strength. Next, we do regression. And I said this, we only do if there's a cause and effect. Otherwise, don't do this. Right. So this is what I did. And results. Where do you look first? Which table do you look first?
The ANOVA.
ANOVA table. We check the p-value. Is it less than 0.05?
Yes.
That means hence BP depends on BMI. BP depends on BMI means what? Slope 0 or non-zero?
Not
Non-zero.
Non-zero. So we know non-zero. Let's go and see how much the B is. That's a B, right? That's a B, isn't it?
Yeah.
Yes.
What's the B value? 2.303.
Yeah.
And look at the P value. P value is less than
Less than
0.01.
0.01.
Therefore, the slope is not zero. If this P value is more than 0.05, that is this slope is close to zero. At the same time, this also be more than 0.05.
0.01.
So number one, the P value, right? Does it depend? Yes.
Yes.
Next question, how? By the equation. Third, explain what is 2.03 means, right? As VP expected to increase by 2.03 for every unit increase in BMI. Next, how much? Fourth step, R square. R square 0.448. What does it mean? 44.8% of the variation in BP explained by BMI. Explained. How much more unexplained? How much more unexplained?
54.2%.
About 45. Unexplained? Explained about 45. Unexplained?
55.
We are partitioning the two. Explained, unexplained. So this is the explained variation and this unexplained variation. We divide the 12 something by the 27, you get that value. This is explained, this total. So 45% explained, balance 55% unexplained. So what happened to 55%? So what happened to 55%? Nakita, what's happened to 55%?
It's affected by other factors.
Is contributed other factors, which is not in this model, in this study. Is 45 enough? Only the researchers can decide. The BMI alone can explain 45%, not more than that. Now, you want to reduce the BMI or reduce? Clinically, you want to reduce the BMI or reduce
BMI.
the BMI?
Yes.
Which is more point to worry?
Worry is
Worry about BP or BMI?
BP.
Again?
BP is worrying.
Yeah, BP are more worried. But here, BP to BMI. Right. So now, let's say the person's BP is 150. How to reduce his BP? Let's say normal BP for him should be 140, right? How do you reduce his BP?
By reducing BMI,
Reducing BMI. How much must you reduce? How much must you reduce? How much must you reduce?
20%.
So now your SBP equals to equation 71 plus 71 plus how much? Okay, let's take 2 now, okay? 2 times BMI. Is 150 SBP very high? SBP 150, is it high?
Yes.
Yes. What's ideal BP?
140.
His BP now is 150. Let's say for his age, ideally must be only 140. Knowing this, how to bring it down? How to bring this down?
By reducing the BMI.
Yeah. How much must it reduce? How much BMI must you reduce? Reduce here. How much BMI must you reduce? Calculate. How much BMI must you reduce? Let's say how much BMI must you reduce? For every unit increase in BMI, how much BP goes up?
2 times.
2 times. So you want to drop BP by 10 points.
20 times. Yeah.
How much this BMI must drop?
20%.
BMI must drop by 20. Right?
Yes.
20 times 2 how much? 20 times 2?
2.
2.
20 times.
20 times the coefficient 2, this coefficient 2.
40.
Forget about the constant first.
40.
20 times 2 how much?
40.
40.
The drop BMI by 20, this BP will go down to 110, right?
Yes.
20. Just now, Giriajan said, drop BMI at 20. 20 times 2 is 40, right? If we do this, his BP will go down from 150 to 110, right?
Yes.
So what's wrong here? What must you do?
So go down only by 5.
By 5. Okay. She says go down by 5. You reduce your BMI by 5. How much BP supposed to reduce?
140.
10 points, right?
Yes.
10 points. So 150 minus 10 points will be what do you have? Understand?
Yes, sir.
Anybody doesn't understand this concept? It's not simply just clicking button, okay? Ideally, his BP is 140. Now it's 150. Let's say now every unit increase in BMI, BP goes up by 2 points. Every unit decrease in BMI, every unit increase in BMI, BP goes up by 2 points. Every unit decrease in BMI
Goes down 2
goes
points.
down. Goes down how much? Goes down how much? By how
2
much?
times.
2 times. 2 points. Now drop 10 points. Therefore, my BMI must drop. BMI must drop by 5 points. Because 5 times 2 is 10. So 150 minus this, I'll get this value. Can you reduce BMI?
Yes.
How to reduce BMI?
Reducing weight.
By reducing weight.
Yeah?
By reducing weight.
Again, simply can't say go reduce a BMI. You can't reduce BMI. BMI is not real. What's BMI equals to? Weight over
Height squared.
height, right? Weight over height, power 2. Now, you want to reduce BMI or reduce weight?
8.
Right. The BMI must be reduced by 10 points. Tell me how much weight you must reduce. BMI equals this. Currently, you must lose 10 points. How much weight must you lose? What question must be asked?
How tall is the person?
How tall the person is. Supposing the person is 2 meters tall. 2 meters tall. This means power 2, huh? 2 meters tall. How much weight must reduce? How much must be the W? Weight?
20. 20 kgs.
20 kgs. You must reduce 20 kg. Doctor can't tell, go and drop 5 BMI. Must ask what's your height. So you must drop 20 kg. That's how the statistics is applied. So you must understand what you're doing. What the application going to be later. Any questions on this? Then why are you going to present this? Somebody asks you this question, you should know what the equation means. Right? All right. Any questions? So that's what I did. And then we check the assumptions. The residuals are random. It's normally distributed. Then it say yes, BP depend on BMI.
But Professor, what about the other factors which will influence the SBP?
That's why I go next.
Okay, multiple. Okay, fine.
Currently we did this simple linear. What do you had here? BMI, BP, SBP. And here we had
BMI.
Which is dependent, which is independent? Which is dependent, which is independent?
SBP is dependent.
SBP is dependent. Why? The arrowhead is closing here, right?
Yes.
You can't see it. Look at the arrowhead. The arrow is ending here, right?
Yes.
Arrow leaving. What's the other word for this variable? When the arrow ends. Arrow leaves. What's the other term used?
Independent.
Exogenous.
Exogenous, arrow exits. And endogenous, arrow ends. Those in social sciences, you may have to use this kind of words. Or read articles, they might have used the words. So this is exogenous. And this is endogenous. Right? Arrow ending, sorry, exogenous. And this is endogenous. Arrow ends. Here arrow leaves. Right? Other term for dependent. Look at the equation. That's how the equation is written. Right? That's how the equation is written. It's a B naught constant, and the B1, and the slope is your regression slope. Now, extension of this, look at the next slide. The extension of this, same like we went from t-test to ANOVA. Look at this now. If I remove this and remove this, basically it's what? Simple linear regression, right?
Yes.
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 Now we have more variables. Rajan, why are we doing this? Why are we adding more variables? Because we want our prediction to be more complete. One variable alone can't explain. When we add variables, we are trying to explain the outcome better. That means R square will increase, right?
Yes.
One variable explains 40%, another variable explains 10%, another variable explains 5%. So your R square will increase. the predictive model becomes better. So here, quantitative. Here again, all must be quantitative. And look at the coefficients. Is a constant, but
Yes.
you need to know what's B2, B1, B2, and so on. Supposing, right, this B1 is equal to 0 means what? This B1 equals 0 means what?
Constant.
The constant, this is B not the constant. If value B1 equals to 0 means what?
Y equal to B0.
B0 means what?
B1 equal to 0 means it is not dependent on x1.
The slope is 0.
0. Yeah.
That means Y does not depend on x1.
1. Yes.
Isn't it?
Yes.
If the B2 equals to 5, means what?
Depends.
Right?
Yeah.
As x2 increase by 1 unit, Y increases by 5 units.
5 units.
Supposing this is -4, that's equals to -4. Means what?
If x increases 1 unit, y decreases by 4 units.
Increases. So this is slope non-zero. Sorry. Just an extension, okay? So this means slope is non-zero. This means slope is non-zero as well. That's 5, non-zero. But this is 0. If I give you an equation like this, I ask you, which variables are associated with y? Does y depend on x1?
No.
No, because why? This must times by 0, right?
Yes.
Yes.
Times by 0, whatever value times by 0. So this value disappears in the model. There is no more. Does y depend on x2?
Yes.
How? Positively or negatively?
Positively.
Positively. How much?
5 times. That's
5 times that.
this
Every unit in
for every unit.
Q, y expected to increase by 5 units, not 5 times.
Okay.
Does y depend on this xp?
Yes.
Let's call it 3, okay? Does it depend on 3? Why? The slope is not 0.
0.
How to interpret this?
Decreases. When x increases by
1 unit.
1 unit,
Y is expected to decrease by 4 units, right?
yes.
Right. So here we'll times by 5. Here we'll times by, so this will be taken out. And this will be times by whatever value, times by -4. The model may come out like this final model. How to interpret this? Y only depends on x2 and x3. For every unit increase in x2, y expected increase by 5 units, and every unit increase in x3, y is expected to decrease by 4 units. One's positive, one's negative. That's exactly what we are trying to establish here. There are several variables here. I want to know each variable. Does y depend on the variable? If yes, how? Questions? Questions? All right. Again, that's what is shown here. We have B1, B2, B3. If the slope of B1 is like this, then you say y depends on x1. B2 slope is like this. Then you say y does not depend on x1, x2 is x3, right? Supposing it's negative, then still y depends on x3, but negatively, positively. They're not related. So we can't see this manually, visually. So what it is now, number one, number two, or number three, which one? You only visualize based on these coefficients. Are they close to zero or far from zero? Far from zero can be positive and can be negative. So our analysis, one click button, will tell you how to visualize this. Is x1 like this? Is x2 like this? Is x3 like this? To visualize. Then write the equation and check the R square and they check the assumption. Now, can you relate this equation to the diagrams, to the figures? Class, can you relate?
Yes, sir.
Right? The B2 0, then the slope is like that. Means y does not depend on x. It's positive, the slope must be visualized like this. Higher the x, higher the y. If the slope is negative, then visualize as higher the x, lower the y. All right, assumptions. Have you seen this assumption before? Sorry, this assumption before? Have you seen this assumption before? Have you done this before?
No.
No.
This one, I think.
A simple linear regression, we did this, right?
Yeah. Independent and
The error term or the residuals. Residuals must be independent and normally distributed, right?
Yes.
This one we've seen already. Now, one additional assumption. What's the assumption here? The x's base values must be independent of each other. That means this should not be highly correlated. Later, I show an example what it means. Right? This variable should not be highly correlated. All right, let's see how that can be visualized. Right, multicollinearity. If this assumption fails, then we say we have a problem of multicollinearity. Multi means what? Multi means
Many,
more.
many, more.
more than
Co means what? Co means
Similar.
together.
co means
So-
together, right?
Together.
Co means together, right?
Yes.
Linearity means what? Linearity means what?
Straight line.
Straight line.
Yeah.
Right. Some of the variables could be highly correlated. And we have a straight line. We should not have this. If the correlation between two variables high, there will be a problem of multicollinearity. How to recognize this, we'll show you in the session later. So this can be assessed by this particular statistics. We call it VIF, variance inflation factor. Now, don't bother about this, how you derive. Come to this, how do you make the judgment? If the VIF less than 5, no serious problem. Assumption is not violated. This assumption is not violated. Go ahead. If 5 to 10, there is a substantial problem. More than 10, there's a serious problem. Right? So we're going to assess multicollinearity using this vector called VIF. And how do you make decision whether it's a problem or not? You look at this, right? You look at this and make a decision. Now here say any two variables very highly correlated. Generally, anything more than 0.9. Anything more than 0.9 is considered highly correlated. So all these going to look at it when you assess as you go. Right? So what do you mean very highly correlated? Anything more than 0.9. Right? So don't have to go detail, click button, BIF come out, you interpret. Maybe I show you first. All right. Look at the last column. That's a BIF. No calculation, just click button. What's the highest value here? Highest value.
8.51.
8.5. Is it more than 5?
Yes.
You put a threshold 5, right? If you put threshold more than 5 is some problem, isn't it?
Yeah, substantial problem.
Very substantial problem. Some authors, they agree more than 10 is a problem. But here I think we'll go more than 5 is a problem. So here, the highest value is more than 5. That is a problem of multicollinearity. In this situation, what do? We see later. Now, let's see another one. Okay. Look at BRF, the last model here in the red box. What's the highest value?
1.427.
Is it less than 5?
Yes.
That means the problem of multicollinearity is resolved. Right?
Resolved as in it's not there.
Say again?
Resolved means it's not there. I mean,
What nothing?
resolved means the problem is not a problem.
There's no problem because the highest value is less than 5, right?
Okay.
That means there's no problem of multicollinearity. Or just put there,
Or they're independent, right?
yeah, no problem of multicollinearity. Right? We call it open scissor or closed scissor. Now take 2 fingers in one hand, all of you. In one hand, just take 2 fingers, open them up, space them, open up. Is it like open scissor? Class,
Yes.
open scissor.
Yes.
Bring them together. Are they very much together?
Yes.
That's what multicollinearity about. Space them out, they're quite independent. Bring them close, touch each other. That's a problem of multicollinearity. So to visualize this, we take these values. As we go to that. All right. Okay. Let's go to example. Same data. Now you want to associate age, weight, BSA, height, and BP. Data is blood pressure. Open the blood pressure data. Blood pressure data.
SBP.
Blood pressure. Right?
Oh,
Blood pressure data.
Excuse me, sir. I don't think we have this data.
Never. Okay, I'll send it to you quickly. Okay. Open the file. Ready?
Yes, sir.
All right. Okay, look at the screen. Actually, what you're asking is, how do these variables associate with the outcome? Age to this. Is it multivariate? Is this multivariate?
Yes.
Hey, this univariate only one, right? Binary, right? Sorry, bivariate, isn't it?
Yes.
We're going to add more and see how it becomes multivariate. Is it multivariate already now? Anything more than one is already multivariate. All right. What do you want to know? What do we want to know?
Whether SBP is associated with age, weight.
All right. SBP depend on age, weight, BSA. BSA is body surface area. BSA is body surface area. So the equation looking for is what? SBP equals to sum B naught, okay, B naught plus age, B1, right? B1 times age plus B2
2,
times
weight,
weight plus
B3,
B3 times
SA,
BSA and
plus
B4, right?
mm,
B4, okay, B4 times and what?
height,
Height. All right.
plus
Yeah, plus some residual, right? Plus what? 4 only, right? This slope for age, slope for weight, slope for BSA, and slope for height, sorry, plus. So BSA is body surface area. Body surface area. Right? Do you think BSA and weight could be associated highly? Weight and body surface area? Fat people, the surface area is it bigger compared to thin people?
Yes.
Right? So we can anticipate a multicollinearity between these two. Right? Later we'll see whether it comes true or not. We can anticipate multicollinearity MC. That we don't know. Supposing, finally analysis, this B1 0 means what? Supposing B1 is 0, what does it mean?
SBP is not depends on age.
SBP does not depend on age. Right? So what I'm going to look at, how this work, the equation, is there any problem? And we're also going to check the residual. Right? If there's a problem, then what do you do? How to rectify it? What to do if there's a problem? Right, basically that's what you're going to do. Ready? So same like before. Number 1, scatter to see. Number 2, correlate to measure the strength. And number 3, regression to get the parameter values. 3 steps. Okay, let's go to the first step. Do exactly what is shown here. Okay, see here, matrix scatter. So matrix There are many variables. There's a mistake here. It's not weight. Go to data. Go to data. Go to variable view. For age, correct this in variable view. Age, correct those, correct here. Right. Age, weight, BSA, and what? Height is not there. Never mind. Use waist circumference. Waist circumference. Our model is no height, waist circumference. Okay. To do the analysis, just run. Right, go to the plot here. Now this plot, there's a mirror image. What do you have? Lower end, same as this end. So just look at one side is enough. Look at the last row. Last row. Right? In the last row, what's the vertical axis? The last row, what's the vertical axis?
SBP.
BP. So this is age, BP versus age. Next one.
Weight versus
This
BP.
is BP versus weight. This is BP versus BSA. This is BP versus waist. Right? Waist circumference. Now, how do you express this BP versus age? Is there a pattern?
Yes.
Is there a positive pattern?
Yes.
Yes. Higher the age, higher the BP. What about weight?
Same.
Same. BSA?
Same.
Same. Waist?
Same.
Same. How many variables here?
4.
Okay. Take your left hand. Open 4 fingers. Left hand, open 4 fingers. The index finger is age. Middle finger is weight. Next BSA. Next waist. Are you okay? Open
Yes.
4 fingers. Index finger is age, next weight, BSA, and waist. Now look at this circle. What's inside the circle? What is this between? This between BSA and weight, isn't it?
Weight. Yes.
Is it very strong pattern?
Yes.
Now take your fingers now. The index finger and your middle finger. Close them. Is it like that? Very highly correlated, right? BSA and weight. Your index finger and the middle finger, close them. Now you can see the models like this. We may have a problem because independent variables, these are independent variables, these two are highly correlated. We can't quantify yet. So roughly we know this. May be a problem. Next, do the correlation. Do exactly what is shown. Okay, the results. Results. You can load of figures, mirror image, take one side. Look at the last row. BP versus, what is this variable? BP versus age. What's the value there? As BP versus age.
0.6.
Is it high?
Yes, it's
Yes. Next. BP versus
Wait.
weight.
weight. Is it high?
Yes.
Next. Now, how come the others not talking in the class then? BP versus
BSA.
PSA. Is it high?
Yes, 0.5.
Correct.
Waste. BP with waste.
All are significant. We say the significant pairwise correlation. Pairwise means what? BP versus age, BP versus weight, pairwise. Still taking two at a time. Now, what is the one in the circle?
0.9. That is.
BSA with weight.
PSA with weight. Is it more than 0.9?
Yes.
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 So we foresee a problem of multipolarity. Okay? Right. Let's proceed with regression. Do exactly what is shown. Age BP dependent. Put all the four inside here. Okay, just this and click OK. Which table do you look at first?
ANOVA.
Wow. Okay, what's the p value in ANOVA? What's the objective? Before that, what's the objective?
To say SPP depends on age, weight, BSA, and or, sorry, waist circumference.
Right. How do you interpret number one? Is a p less than 0.05?
Yes.
Yes.
Listen, BP depends on at least one of the four. Don't say BP depends on all four. BP depends on at least one of the four. What's the next question?
Which one is depends?
Yeah, go to number two. Look at the p value in the last column. So which one is not?
So in my table, ANOVA table, the SIG or the p-value is directly appearing as less than 0.001. Like it's not appearing as 0.000.
Appearing as what?
Less than 0.001.
Your latest version? What is your version? Version 27 or what?
26, I think.
No, it's okay. Still less than 0.05, right?
It directly gives you this value and not the exact value then, right?
Okay, maybe the latest version, okay? Okay, next. Look at the last column under the SIG value, p value. Is A significant?
Yes.
A significant?
Yes.
Yes.
PSA?
Nope.
Or waste?
Yes.
P value less than 0.05. BP depends at least one of the four. Which one or which ones? BP depends on age, weight, and waste only. You write the equation. You write the equation, same like before. You take this part and write the equation. Right? So as BP equals to 48 plus 0.5.
68.
Right. So take the 48. That's 48 is a constant. Constant goes there. Next, 684 for age, and that's for weight, and that's for BSA, and this for the waist.
Since it does not depend on BSA, then why do we consider it in the equation?
Now, but still, from this table, whatever comes here, you write this. So later we'll see how to get rid of the BSA. You can't simply drop BSA here, right? Since not significant, you can't simply drop here. A lot of changes take place. Don't do this yet, right?
Yes, Prof.
Explain as it is first. How to interpret? Look at below. For every unit increase in age, BP expected increase by 0.8684 units. This last statement important, provided other variables remain unchanged. For every unit increase in age, BP expected to increase by 0.684 units, provided other variables remain unchanged. So what does it mean? Supposing a person is 40 years old now, 40 years old, and currently is 40 years. Next year will be 41. Provided the weight, BSA, waist all did not change, when it goes from 40 to 41, 40 to 41, is BP expected to increase by this much. This statement is very important, provided others remain unchanged. Just aging alone would solve so much. Question? Question? Next, how to interpret weight? How to interpret weight?
In terms of kgs.
Supposing within the year, same age, BSA and waist, the weight goes up, let's say currently weighs 78 kg, and it goes up by 1 kg, become 79, is BP expected to increase by this much?
Yes, if others remains constant.
Right. Okay, that's how I explain. Provided others remain
Unchanged.
So number 1, number 2, number 3, write the equation. Number 4, interpret. And number 5, R squared.
Prof, do we need to interpret the BSA as well?
Yeah.
Oh, we still.
Whatever written must.
Yes.
Right. Later we'll see the simplified model. Only whatever the model must write. And R squared. How much is R squared?
0.636.
What does it mean? 63.6% variation in BP explained by the 4 predictors. Why? The model learned there are 4 variables still there. Even the BSA is not significant, still there. Okay, you can't say only the 3 variables. Here also 4 variables. Even though it's not significant BMI as BSA, still include the equation, still interpret, and still 4 predictors. Questions? Right. Among the variables, which is most important? Among the variables we consider, which is most important?
BSA.
BSA, why?
It is 9 times. 9 units, it will change. The change in waste.
Right. We don't make conclusion based on this. That's why age is measured in years. Weight is measured in kg. BSA is measured in meter square. Waste is measured in centimeter. Don't say, so relative importance, we go to beta, standardized. For relative, this only for writing the equation for prediction purposes. For testing for relative importance, look at the beta. It's the highest value. This is the highest value here.
Age
Age.
0.32.
You want to rank the variables in terms of levels of importance. Age, number 1. Number 2,
Weight.
weight. Number 3,
Waste.
Waste.
and BSA is the last. Okay? It's only for writing the equation for prediction purposes. We want to know relative importance. What relative importance? Which one to tackle first? Right. Age, weight, waste, followed by BSA last. Okay? So some of the variables are modifiable, some are not. Can you reduce age?
No.
Can you reduce age?
No.
No.
Age is not modifiable. Can you work on the weight, reduce weight?
Yes.
Yes. BSA, when the weight goes down, BSA will go down.
Yes.
The waist also exercise will go down. These three are modifiable, first one is not. This is all important for you to write your project work or your thesis. Understanding what actually these table values are. Right, next, testing assumption. Okay, can you go back and redo this? Okay, so after doing this, go to statistics. Right, select statistics. Right, this is the one collinearity diagnostics. Okay, collinearity. Continue. And click OK. So now look at the last column under coefficients. So until here, look at the last column, VIF. What does VIF stand for?
Variance inflation factor.
Yeah. What is it used to test? Test for
Collinearity.
multicollinearity.
Collinearity.
How do you read this? Any value is more than 5, there is some problem. But here we know there is some problem. From beginning, from the scatter plot, we foresee this. From the scatter plot, we saw there could be problem. Correlation, we saw is very high. And now it shows you, look here, there is a problem. Okay, next, what do you want to know? There's a problem. Next, what do you want to know?
What problem?
There's a problem. Problem of multicollinearity. That means assumption is not met. Assumption independent not met. Next, what do you want to know? What to do?
Testing the assumption.
Yeah, just now we said these two probably were highly related. We found yes, there's a problem. The model is not valid. Whatever this model is not valid. So what's the next question? What must you do? Isn't it? What to do to rectify this, right? Currently we're having a problem, right?
Yes.
Model is not valid. What to do? What to do next to eliminate the problem? Now, what can we do manually? What can we do? Knowing which variable is giving trouble. Which variables are giving trouble?
BSA.
Weight and BSI.
And weight. So what shall we do?
Approximate them or something.
What shall we do?
We can put some approximation values, like not consider them.
Drop either one. Isn't it?
Yes.
If they're jointly problematic, then drop either one, right?
Yes.
Which one?
Doctor, how do you know which one to drop?
How do you know? Just asking. Which one?
No, BSA depends on weight. So weight we can drop.
Which one is easier to measure? Weight or body surface area?
Weight.
Weight.
Weight. I may sacrifice this. Right? It stands on the balance. You already know this. Body surface area, we need special equipment. The other option is, let's see SPSS can help us or not. Under method here, pull down, look at stepwise. In most cases, the software can help us to eliminate the problem of multiple in most cases, but not in all. So in your notes, that's what I'm going to do. Right? Stepwise regression. So you're going to change this method to stepwise and click 36, you put R square, change. So do it now. Change the method stepwise. That means you're telling SPSS step by step, take elements, the variables one by one, and tell me how many variables need to be included. And then go to 36, click on R square change. Continue. Click OK. Just follow the notes. Let's see what happens. Look at the first table, variables entered or removed. Variables entered or removed. Column number 2, model 1, age. Model 2, weight. Model 3, waste. Look below here. Model 1, age. Model 2, age and weight. Model 3, age, weight, and waste. So step by step, first variable age went in. Next step, weight went in. Next step, waste goes in and stops. Which variables eliminated? Which variable is not there?
Body surface area.
Yes, area.
Is it good for us?
Yes.
The base and BSA were working some noise, isn't it? All right. Take the next table. Model 1, R square. How much R square? Model 1, how much R square?
0.46.
46.5%. Look below that. Age alone explains 46.5% of the variation BB. Right? So 46.5%, that's the R square change. Now, over and above age, next variable, which variable comes in? Which variable next? What's model 2?
Weight.
You know here, what's model 2?
Weight.
Weight joins in. If weight comes in, what's R square now? What's R square now?
0.6.
Is it bigger?
Yes.
Is it higher?
Yes.
This is Model 1. Model 1 refers to age. This model 2, meaning age and weight. Age alone, 46.5%. Age and weight, 60%. How much increment here? How much increment?
14.2.
Okay, look at this column here. Right? Age alone, 46.5%. And you bring in weight, there's additional increase of 14%. So that's why you have total this much.
Yes.
Next variable, model 3, refers to
Age, weight, waist.
weight, and waist. The 3 explain how much?
0.6.
63.6%. Of that, 0.03 is brought in by, explained by weight.
3%.
The model 3 is waist, right? Plus,
Yes.
right. So now, weight adds in another 14%. Waist adds another 3%. So total is 63.6%. Now compare the previous model. How much was explained? In this model, what's R square?
63.6.
63.6. This current model, what's R square?
Same, 63.6.
That is right. The BSA hardly explains anything else, right? Anything, right?
Yes.
4 variable does not explain as much as the 3 variables here. So BSA can be dropped. And it didn't drop manually. SPSS helped us drop it. Right. Let's see the assumption of multicollinearity. Now this refers to first model, age came in. Second model, weight came in. Third model, waist came in. So we concentrate only on the last model, in this case, third model. This is how step by step is done. So now, the final equation, this is the final equation. BSA is no more there. We can't simply delete just now. We can't simply delete BSA and say that's my final equation. Let's see how much difference. Okay, just so somebody asked, can I just delete that variable? Where is it? Got that? So I'm clicking this. If I taken this and deleted BSA, compared to here, are the values same or different? Are the values same or different?
Different.
Right? Look at the coefficients. Right, 68.4, maybe about the same. Here 61, 611, here's different. 974, right? Slightly they're different. So we can't simply drop BSA and say that's my equation. You must rerun. So don't do this. Right. Are they all significant? Look at this one here. Are they all significant? All the 3 variables, are they significant?
Yes.
Yes. What about BF? Is it less than 5, highest value?
Yes.
Less than
So
5.
can I say this?
Yes.
Yes. So VIF, the problem has been resolved. So that's my final equation. The moral story is you don't have to find the person's BSA, no need. Just this alone, these 3 variables alone is enough. Enough means what? How many percent? 63.6%. We explain the variation in SDP. Questions? A simple write-up. Report the results. Your thesis, whatever, don't copy. Sometimes what they do, they copy all the tables and put inside there. Imagine how many tables. Copy this table, put it inside there. Copy this table, table after table after table. We like the table so much, put then appendix. See whether precisely we are reporting what is needed. Now, what's the objective? What's my objective?
To test the association
Association
of
of
SPB
weight or
with age, weight, BSA, and waste.
right? That's tested, huh? No rested. Tested. Okay. Multiple regression. Results are shown in table X. Tell them these are results from this table. First, don't put a stepwise only. Start with enter first. Start with this. Right? So each variable, write this until VIF. So don't have to show the, we don't have to show the tolerance. Take out this, don't have to show tolerance, just VIF. Actually either one, but this is more informative. VIF derived from here, so don't have to show that. Just take this only, okay? So write up, associated table X, SBP was associated only age, weight, and waste because this is not significant. VIF value 0.851, highest value 851, which is more than 5. Hence, there was a problem of multicollinearity. We still have to write the initial equation. Equation write according to this. Right? So write it. Here you don't have to mention for every unit increase in age, BP goes up with no need. That is for us to interpret. R square value. I didn't put a table here, right? R square value is this, which means this, by the 4 predictors. Now all this until here, stepwise, the enter method. But we know there's a problem here, and we know there is one variable which is not significant there. So in stepwise analysis, only age, weight, waste were significant. And the R square value this much, what does it show? Is it much different from the enter method? That R square value, is it much different from here?
No.
No. Check the residuals. And then finally, that's my equation. Right? A simple write-up. You want to put keep all the tables, put appendix. Some students put an ANOVA table. Right, they want this, all the tables, copy and paste only. They don't even label the tables. What is this table? What is this table? But basically, I want to know information. What's telling us? What's telling us and what's telling us? Right? We're not calculating manually. Okay? Okay, let's run this one more time. Whole thing. Start all over again, regression. Ready? Class, are you ready?
Yes, Prof.
Right. Analyze, regression, linear. Reset. Click reset. Okay, what's the dependent variable?
SBP.
SBP. Dependent.
Age, weight,
BSA.
BSA waste.
So what else we're doing? We'll be checking for statistics.
Collinearity.
R squared. No.
Right, that's okay. Right, we don't have to go into that. Right? So I showed you how it works. That's all. Polarity. Next, plots. Reset and received and predicted. Clear? Safe, unstandardized. Setting all in one go. I do one more time. Reset. I want to know whether SBP depends on age, weight, BSA, and waste. I also want to know whether there's a problem of multicollinearity. And I want to see whether the assumption of the residuals being independent is met or not. Always received and predicted. And I want to save the residuals to test for normality. So, finish. Okay, currently, if you look at ANOVA table, there is a yes, BP. BP depends on at least one of the four predictors. Which one? You can see that all except for body surface area. Is there a problem of multicollinearity? Yes, values are high. Can I write the equation? Okay, write the equation based on these two. Next, what's R square? R square here, so what does it mean? So now one assumption here is not met. Next, residuals. Is pattern random? Residuals, are they random?
Yes.
Yes. Next, are they normally distributed? So I'm going to test for normality. Explore. Test for the last variable we created. And then plots. Normality plot with test. Continue. And click OK. Look at the table. ASSW.
Yes.
Yes. Right? Assumption on the residual is met, but not the VRF assumption of multipolarity. So this model is not valid. So next, we try stepwise whether this will help in any way. So change to stepwise and just click OK. So this tells you step by step. Step one, the model one refers step one, age came in. Over and above age, next step, weight comes in. And the third step, waste comes in. BSA was not admitted. This model summary. First model is age alone, 46.65%. Age and weight becomes 60.7%. Age, weight, and waste, 63.6%. You don't have to look at ANOVA. Come to coefficient. In this coefficient, we only need the last, right? We don't need the 1, 2, 3. We don't need this. Right? So only check out the last one. Right. So write the equation. This is the final equation. And the problem of multicollinearity resolved. Among the three variables now, which is most important variable? Which is relatively more important?
Age.
Now, can I say based on this, right? Can I say based on these two? How many times more? Waste is how many times more compared to weight? How many times more?
Should we be saying unstandardized B or standardized?
Here, how many times more? Is 0.6. How many times more?
Roughly 9 times.
9 times? 10 times only 61. Isn't it? Let's say about 15 times, all right?
Yeah.
But that's not true. Look at this now. Okay, look at this now. Can I say age is twice as important as waste?
Yes.
Yes, because they are standardized the unit less. So this is for checking for relative importance. This is for writing equation for prediction purposes. And look at the assumptions. These are random. And check the residuals. Is it normal? Right? Okay, it's normal, more than 0.05. So whatever it is, ultimately, you must learn to present it in a simple, concise manner. Where is it? That's my write-up. I delete it. Okay. So now you're going to do, now's your part. Which variables shall I choose? Blood pressure data. I want you to model DVP. Same data, same predictor variables. Just now we did BP, SBP. Now you model DVP. Are we clear?
Yes, Prof.
What are you going to do? After doing all this, you're going to send me a report exactly like this. That's all I want.
Yes, Prof.
I give you 1 hour, right? Now it's what, 5 o'clock. I want the results by 6 o'clock or even 5:35. How long does it take? Just now I did it, how long?
15 minutes, like
15
10
minutes. Somebody timed, okay? 15 minutes, that's all you need. Right? So do this, prepare your result, your reporting in Word file and send to me now.
Yes, Prof.
Right? Any questions? Let's stop recording now.